Hey guys, this is 11.3 day 1. Today we're going to talk about the normal distribution. So we've been talking about distributions for a while now, and we've been graphing them with, looking at them through box and whisker plots and also histograms. There should be a U here. We're going to focus a little bit on the histograms right now, but sort of extend that. The histograms you've drawn till now have had, I don't know, like at most what, like 5, 6, 7 bars. Okay. Well, that is not very realistic, right? Now, and the data that we've had, right? How many numbers has there been in our data? I mean, at most, what, 30 data points, 40 data points? You know that that's not a good enough sampling to make any reasonable conclusions. What we really have to do is we have to increase the number of data points, okay, in order to really take a look at in order to really see what we're looking at. So suppose you did increase the number of values. So let's take a look at these 4 curves here for a minute. All right, I have this one. There are 100 values in the data set from which that histogram was made. And then if you look over to the right, this one, look, I have 1,000 data points, and you can see how I have a lot more bars, right? 1,000 data points will result in a lot more bars because you're going to have a lot more classes. Well, now if I increase to 10,000, look at what that looks like. Right? And now you see here how we are dealing with a symmetric distribution around the mean, right? It's a symmetric distribution. So we're taking a symmetric distribution, and now we're looking at, if you had 100 data points, 1,000 data points, 10,000 data points, and now imagine if you had like 1,000,000 or 1,000,000,000 data points, what would happen? This would be even thinner, right? These bars would be even thinner, and then what you would end up with is a smooth curve like this one. And so you see here where this is n equals a population, millions, okay, hundreds of millions. So you get a distribution that looks like that. Okay, and that is what a normal distribution is. So if we go back up here, the normal distribution is basically a continuous probability distribution. By continuous, I mean I don't have individual bars. I have a continuous curve like the one we see on the bottom right. All right, so let's talk about some properties of the normal distribution. First and foremost, the graph is bell-shaped, right? You see that? It's a bell, and it is symmetric to the mean. So we also say we call it a bell curve, and I'm sure you've heard that term before. Okay. In the normal distribution, the mean, the median, and the mode are all equal to each other. There is some repetition here. And they are all located at the center. Okay, so if the mean is 53, so is the median, and so is the mode. All right. We said the curve is continuous. The curve approaches but never touches the x-axis at the very bottom here. It approaches the x-axis but never touches it, similar to our exponential functions. The total area under the curve is equal to 1 or 100%. All right. So if I say, okay, let's say these are SAT scores, right? This bell curve will represent 100% of the possible SAT scores, right? So all of your data points are included in here. Okay. All right. So now let's talk about standard deviation. We've talked about standard deviation a while back, and at that time we said it is a measure of how far a random data point will stray from the average or the mean. Okay, so again, that's just a measure of how much values differ from the mean. Okay. Standard deviation is very, very important when we talk about the normal distribution. The standard deviation, like we said, measures the variation. If values are very, very close together, they have a small standard deviation, but values with more variation will have a larger standard deviation. So if the average on a test was an 83, and if, all the scores, ranged from, let's say, 80 to 87, all the scores are close to the 83, there is a small standard deviation. But let's say if the average was an 83, and then you've got scores in the 60s and the 50s and the 90s and 100, they're spread apart, large standard deviation. Standard deviation has the same units as the original data. Okay, so let's talk about this term for a minute. If I have a data set, right, a value is considered unusual if it differs from the mean by more than 2 standard deviations. Okay, and so we'll talk about that in a little bit. And we can compare standard deviations of 2 data sets only if they use the same scale, right? So you can't, if you're measuring one thing, if you have heights of girls and boys, but you measure the girls in centimeters and the boys in inches, you cannot compare them. Okay, let's talk about the shape. Okay. The shape and distribution of the shape and the position of a normal distribution depends on the mean and the standard deviation. Okay. If there is a larger standard deviation, this means the data values are spread apart, then the curve is wider. All right, so here you see these two, right? Look, this is the mean, mu, that's a Greek letter mu, it makes the m sound. That's the mean. So look at the red and the blue here. They both have the same mean. However, one of them, the red, right, has a larger standard deviation, which means the data values are further apart, right? So if the red was our test scores, you've got a lot more further away from the mean. And how could you tell that they have the same mean? Because their peaks are on the same line. Okay. When the mean of the data set changes, the graph will shift horizontally. Okay, so suppose I graded a whole bunch of tests and I got this blue curve with a mean of, let's say, I don't know, 84%. And then 3 people were absent. They came, they took the test, they all aced it. Now the mean increased. So what happens is the entire curve shifts further to the right. Okay, so from here to here, you have a higher mean. All right. So let's talk about the empirical rule. This is a popular rule. Everybody knows it by name, all right? The empirical rule. For data sets having a normal distribution or a bell-shaped distribution, these are the properties that apply. 68% of all values fall within one standard deviation of the mean. Okay, so suppose this is the mean or the average of the test scores. And suppose the standard deviation is 5 points. Okay, so I go to the right by the standard deviation 5 points. I go to the left by the standard deviation 5 points, or the standard deviation. And then when I shade that area, right, 68% of all of the test scores are going to fall within these values. All right, so suppose the average was 85%, and suppose there was a standard deviation of 5% for argument's sake. Okay, so from 85, I go to the right 5%, and that's 90. Then I go to the left from 85, 5%, that's 80. So when I have all the tests, 68% of the students' scores are going to fall between 80 and 90%. All right, one standard deviation. Now, if I go further out, 2 standard deviation. Now, if I go another 5 and another 5, right? Let's see what happens then. Now I've gone 2 standard deviations. 95% of the test scores will fall within 2 standard deviations. Okay, and it's very symmetric. 34% lies within this region, 34% lies within this region, and then another 27% lies on the outside. What's 27 divided by 2? 13.5. So 13.5 lies here, 13.5 lies here. So given our former example, remember how I said this was 75 and this was 95? 95% of all of the students' scores are going to fall within those two values, 75 and 95. So if I have a 100-person class, 95 of the test scores are going to be within that green shaded area that I shaded green here. Now, if I go 3 standard deviations, right? If I go 3 standard deviation, another 5 units over and another 5 units over. So now I'm going from 70 to 100. Now it's 3 standard deviations over. 99.7% of the data is going to be within those 3 standard deviations. So out of 100-person class, 99 of the data points, 99 scores are going to fall within a 70 and 100, okay, for a normal distribution. So the added part here, okay, from the 2 standard deviations to the 3 standard deviations, look, it's a very tiny amount. Before it was 95%, now I added 4.7, right? So half of it lies here, 2.4%. Technically, it's 2.35, and then 2.35% here. We're going to go with the 2.4, all right? We're just going to stick with 2 decimal places. And then past that, in the little regions here, you have 0.1% and 0.1%, and that's 100% finally of all the data. Okay, now this formula, this empirical rule, is also called the 68, 95, 99.7 rule. Okay, I know it's a mouthful, but man, these people who, like these statisticians, oh my gosh, they love going around talking about the 68, 95, 99.7 rule. All right, and that's what they call it. 68, 95, 99.7 rule. Okay. So let's do a couple of examples here. All right. IQ scores have a bell-shaped distribution with a mean of 100, so that's important, and a standard deviation of 15. What percentage of IQ scores are between 70 and 30? Okay, so the first thing you're going to do is you're going to draw this distribution. Always. You're always going to sketch this distribution. And you know what? It's not that tough to sketch the distribution. Apparently for me, the toughest part is to draw a straight horizontal line. There you go. So you draw a horizontal line. That's the axis. You draw a bell-shaped curve as best as you can. In the middle here, you put the mean. It's 100. Okay? And it says there is a standard deviation of 15. So now what you do is you go over to either side 15 points. So plus 15 is 115. Minus 15 is 85. I want to keep doing this until I get 70 and 130 somewhere. So let's go one more standard deviation. So right now, this is one standard deviation from the red to the red. These are all the values that fall within one standard deviation. Let's go one more. Minus 15, I get 70. Plus 15, I get 130. And there you go, right? So now, from here to here, I went over 2 standard deviations. 2 standard deviations. 2 standard deviations corresponds with, what's the rule? 68, 95, 99.7. 2 standard deviations is 95%. So we say 95% of the scores lie within 70 and 130. All right, let's do another one. The heights of the 880 students at East High School are normally distributed, okay? Normally distributed, meaning it's a normal distribution. That's what it means. With a mean of 67 inches and a standard deviation of 2.5 inches. All right. Okay. About how many students are more than 72 inches tall? Okay, so first we draw. We draw a cute little bell curve. The average, or the mean rather, is where? 67. Now, standard deviation of 2.5. So now we're asking how many students are more than 72 inches tall. So I really don't need the left part of the graph, right? So let's just go over here. I add 2.5. Now I'm at 69.5. And then I add 2.5 again. Now I'm at 72. Okay. Now, how much is this, right? Until here. How much is it until here? Well, okay, so let's take a look at this for a minute. We want to know how many students are more than 72 inches tall. So we want to know how many students fall within that category. All right, so now how many fall until, like, how many students are there to the left of this curve? Well, do you remember what we had said here? How from the middle, it's 34 and then 13.5. So this is 34%. This is 13.5%, right? And how much is this entire thing? Is that half of the data? That's 50% of the data, right? So I can do that blue part is 50% minus 13.5 minus 34, and that's a total of 880. I'm sorry. How many is that? Is that 2.5%? Okay, so now that's 2.5% of the population. Well, how much is that? 2.5% of 880 students is, I have to make this into a decimal, 0.025 times 880. That is 22. So I have 22 students above 72 inches tall. Now, another question, same problem. What percent of the students are between 59.5 and 69.5 inches tall? So I'm just going to draw it again. Oh my, okay. So my median is 67. All right, 59.5 and 69.5. So 69.5 here, that's one standard deviation. Now, let's go over minus 2.5, that's 64.5. Another one, minus 2.5, that's 62. Another one, and I get 59.5. Okay, so I want the region, I want the number of students, or the percentage of students between 59.5 and 69.5. Okay, so what are the percentages that go in here, right? It's always, the middle here are 34%, 34%, and then going outward, it's 13.5% and 2.5%. Or, sorry, we said 2.4. So altogether, that's 34 plus 34 plus 13.5 plus 2.4, 83.9. So it's 83.9% of all of the students. Okay? And with that, you can go ahead and do the homework. So just make sure every single time you draw the distribution graph, do the standard deviation, put in these numbers, and then you can just add, whatever ranges you're being asked for. All right, have a good day, everybody.